As the time will pass, you will get to know that it is actually much easier to solve a signal flow graph compared to a block diagram, and the reason is Mason's gain formula. By using this simple formula, you can find the transfer function of an overall system quite easily through the signal flow graph. Mason's gain formula for the determination of the overall system gain is determined by summation of different path gain multiplied by the value of signal flow graph determinant for the part of the graph not touching with the kth forward path divided by the signal flow graph determinant. The triangle is representing the signal flow graph determinant, which is also referred as characteristic function of the signal flow graph, which can be found out to be equal to 1 minus sum of loop gains of all individual loops plus sum of gain products of all possible combinations of two non-touching loops minus sum of gain products of all possible combinations of three non-touching loops, and this pattern will go on. The most important parameter which you have to remember is the determinant of the signal flow graph. It is a very important parameter which you must remember at all times and should not be feeling lazy while finding out this expression, even though it is quite lengthy. From the formula itself, you can clearly say that it is very important to be clear about what are non-touching loops. Before I move forward, it is very important to discuss few confusion zones which confuses a lot of students. This is a signal flow graph which I have taken for reference. You can clearly see there are in total 3 possible loops in this signal flow graph. My first question for you is, are the two loops, loop 1 and the loop 2, non-touching loops? You have to simply answer in yes or no. Take 15 seconds and tell the answer as per your understanding. The answer is yes. Many students try to connect different topics from different subjects. Like for example, here many students try to connect the topic of touching loops with the concept of circles like intersecting circles, concentric circles, but in control systems, the definition of two non-touching loops is there should not be any common node between the two loops for the loops to be non-touching loops, and that condition is valid here. The loop 1 consists of two nodes x2 and x4, whereas loop 2 consists of two nodes x3 and x5, and as such there is not a single node which is common to the loops loop 1 and loop 2, even though the loops are intersecting each other, but still they are non-touching loops. The second question is, are the three loops loop 1, loop 2, loop 3 non-touching loops? Again you have to answer in yes or no within 25 seconds. The answer is no here. This might be a little bit difficult for you to determine. Let me clarify it for you. If you are taking all the three loops together and trying to find a single node which is common to all the three loops, then your approach is actually wrong. For the three loops, loop 1, loop 2 and loop 3, obviously we are not having a single node which is common to all the three loops. The node x5 is common to only two loops, loop 2 and loop 3. But this is not the way that you should be approaching. You have to check all the three combinations, loop 1, loop 2, loop 2, loop 3 and loop 3, loop 1 also. The pairs of these loops also must not be having any common node. Then only we can say the three loops are non-touching loops. But since x5 is a common loop for loop 2 and loop 3, so we cannot say the loop 2 and loop 3 are non-touching loops, and that's the same reason we cannot say the group of three loops, loop 1, loop 2 and loop 3 are also touching loops. The moral of the story is, if you have two loops which are touching each other, then there is no way we can have a group of three or more number of non-touching loops consisting of those two loops which are touching each other. All the different pairs within a group also has to be non-touching loops. You will get more clarity while solving problems, but still I am giving you a little bit idea about the mistakes you might commit in solving the problems. Now let's see the limitations of Mason's gain formula. The Mason's gain formula is invalid for self-loop of unity gain. If such conditions arise, then you have to ignore the self-loop irrespective of where it is present. The second limitation of Mason's gain formula is that it is invalid for self-loop of any gain at input node. Here also you have to simply ignore the loop present at the input node. Read the two statements very carefully. At input, self-loop of any gain has to be ignored. Whereas if you are talking about any other node, then self-loop of only the unity gain is to be ignored. After ignoring these loops, you can simply solve the remaining circuit for finding the overall transfer function of the system. There is another advice which I want to give you. If there are any outgoing branches on output node, then extend the output node by introducing a dummy node. It is actually not a limitation of Mason's gain formula, but I have seen many students committing mistakes and getting confused by this. It will be much better if you extend the network by introducing a dummy node, and by doing this, you will be reducing your chances of committing mistakes significantly. After applying the limitations and the advice, we will have this resultant signal flow graph, of which we can easily find the overall transfer function by using the Mason's gain formula. This subject is a numerical based subject. You have to solve a number of problems, then only you will get confidence and idea about the different variety of questions that are possible in this subject.